Assalamu alaikum wa rahmatullahi wa barakatuhu. How are you all, my dear children? In today's physics class, we will be learning the rest of the chapter, which is magnetic effects of electric current. Starting with the dua, Rabbi yassir wa la tu'assir wa tammim bil khair wa bika nasta'inu ya fattahu Rabbi zidni ilma, Rabbi zidni ilma, Rabbi zidni ilma. In the beginning of the chapter, we had two pictures. In your textbook, what were they? Firstly, they showed the picture of a bar magnet. Secondly, it was the picture of an electromagnet. And what is the difference between a bar and an electromagnet? Here in this picture, you can see that the magnetic field lines, which are imaginary magnetic field lines, starts from the north pole and end at the south pole. Starting from the north and ending at the south, outside the magnet. The magnetic field lines inside the magnet will be from south to north, so that the loop is closed. This is an electromagnet. Let us see what is the difference between these two. Okay. A bar magnet is also a permanent magnet. Okay. The bar magnet or the permanent magnet will be made of a material having magnetism naturally magnetized material, and it creates its own magnetic field which is persistent or permanent. It creates its own magnetic field which is permanent. But in an electromagnet, the type of the magnet in which magnetic field is produced is only by electric current, which means a substance becomes an electromagnet when current is passed through it. When current is off, that won't be a magnet. If current is on, it will act like a magnet. That is what is an electromagnet. In a permanent magnet, the north and south poles cannot be changed. But in an electromagnet, if we reverse the direction of current flowing, the polarity, north pole and south pole of the magnet changes. In a particular direction of current, one will be north and one will be south. In the reverse direction of current, the other will be north and south. Right. Permanent magnets are made of hard materials and electromagnets are made of soft materials. Permanent magnets are made of iron, cobalt, nickel or ferromagnetic materials. Okay. In a permanent magnet, the magnetic field strength is constant. We cannot vary the strength of magnetic field, but in an electromagnet, which we will learn in this chapter, the strength of magnetic field can be varied and it can be applied for many things. The strength of magnetic field, the field strength can be varied, which is very useful. Permanent magnet example, Earth has a permanent magnet. Electromagnet example, it a solenoid or a coil which is wound across a nail, an iron nail or any nail, and connected to a battery. It is an example of electromagnet. When an iron nail is wound in a copper wire and we connect a battery to it and pass electric current, then iron nail will act as an magnet. This magnet will be called as electromagnet. Okay. Then we discussed about Eastern conducted an experiment, and by chance there was a magnetic compass sitting under the current carrying conductor. It deflected. So AB is the conductor here. Magnetic needle is placed under the conductor. It deflected. So let's look at the circuit diagram. This is the circuit diagram. The magnetic needle is placed under the conductor. First point is current passes from positive terminal to negative terminal. So here the current is passing, this is the south portion, this is the north portion of the needle. So current is passing from south to north in this diagram. To which side will the north pole of the magnetic needle deflect? We learned that using Ampere's swimming rule. There is another trick also. Learn the word snow. Snow rule. S-N-O-W. Snow rule means when the current is passing from south to north, the magnetic needle will deflect over west. S-N-O-W. Snow rule. This is for only normal when the conductor, when the magnetic needle is below the conductor, normally. And when the current is moving from north to south, that is, we reverse the polarity of the battery. What happens? The north pole of the magnetic needle deflect towards east. Right? Okay. Snow rule, what is that? South to north over west. What was the Ampere swimming rule? Let us revise. If a man swims along current carrying wire such that his face is always towards the magnetic needle, face is always towards the magnetic needle, through which the current is entering his feet. Current is entering the feet, leaving from the head. Current is entering the feet and leaving from the head. Then the north pole of the magnetic needle is always deflected towards his left hand. In this picture, magnetic needle deflected towards west because his left hand is in the west direction. Okay, there are two cases, right? When we are facing, the man is facing downward, the magnetic needle is kept below. See, that is normal swimming. What is backstroke swimming? When the magnetic needle is placed above. He is facing the magnetic needle, but magnetic needle is placed above the conductor. This is backstroke. In normal swimming, let us look. Where is his left hand? When he is moving from south to north, his left hand is in the west. When he is moving from north to the south, his left hand is towards east. In backstroke swimming, he is facing, see his eyes and face. Yes. In backstroke swimming, the needle deflecting towards the left hand, which is east, current carrying south to north. In backstroke, the magnetic needle is placed above, which is important. Magnetic needle is placed above the conductor. Here also magnetic needle is placed above the conductor and the current is flowing from north to south. These two conditions are required for the magnetic needle to deflect towards left, that is towards west. Okay, note this diagram. Then we have told that we should know about a straight current carrying conductor. In a straight current carrying conductor, the current is flowing from A to B, right? Then how do we know magnetic field direction? There will be magnetic field around this current carrying conductor, right? How do we know? What is the rule? This is the rule, which is called Maxwell's right hand thumb rule, right? Yeah, from A to B, magnetic field lines will be in the anti-clockwise direction. Let us look at the rule. Imagine you are holding a current carrying conductor with the right hand in such a way that thumb is pointing in the direction of current. Then the direction in which the other fingers encircle the conductor will give direction of magnetic field. So right hand must be held in the conductor and thumb must point the direction of current. Then the fingers encircling the conductor will show what? Magnetic field direction. Right? Right. See, thumb, magnetic field direction. Right? Okay. When the current is flowing from south to north, anti-clockwise direction. When the current is moving from north to south, that is downward. Downward means clockwise movement of magnetic field. Upward movement means anti-clockwise movement. Okay, note these two figures also. Upward movement of current means anti-clockwise magnetic field. Downward movement of current means clockwise magnetic field direction. Then we are saying that magnetic needles are placed one above the conductor and one below the conductor. We know that if we place above the conductor, then we have to look backward swimming. And if we place below the conductor, then we should do the normal swimming. So let's do the normal swimming first. Normal swimming, current is up, south to north. Snow rule, S-N-O, west. Snow rule. So it deflected towards west. When the magnetic needle is upwards, then it deflects towards east. Okay? Yes. Look at the palm and look at the fingers. Palm is going backwards. Look at the arrow mark here in the magnetic needle. The arrow mark in the palm and arrow mark in the needle is in the same direction. And arrow mark in the fingers and arrow mark in the above magnetic needle is in the same direction. See? Yes. This is an extra point, right? Okay. And what is this picture? This picture comprises of a conductor. Current is moving from south to north, that is up. And we are drawing a path. We are keeping magnetic needles at points. See, when the magnetic needle is here, it deflects towards this direction. When it is here, it deflects towards this direction. That is the north. So when we draw a path, when keeping the magnetic needles at different positions, we can create a circle. So this shows that magnetic lines are at circles. Magnetic lines are concentric circles around the conductor. Now we told that we have to study about a loop also. We studied about straight conductor. Okay, we finished that. Now we have to study about a current carrying loop. So how do we say current carrying loop? Take a picture. The point here is P and the point here is Q. At the point P, the current passing from P to Q. That is, note that the current passing here is clockwise direction. In this picture, current carrying is in the clockwise direction. You can see current is carried in the clockwise direction. Yes? Yes. From P to Q. In this side. Okay. Hold your right hand on this section. You can see that the magnetic field is into the coil at the center of the coil. Don't look outside. Look at the center of the coil only. Into the coil. All the arrow marks are into the coil. Place your right hand downwards here. What happens? Here also, the magnetic field lines move into the coil. So at the center, when the current is flowing from P to Q, that is, it is flowing in a clockwise direction, we can see every magnetic field is moving into the coil, right? Right. When the magnetic fields are moving into the coil or into the magnet, what pole is that? Into the magnet means south pole. Into the magnet means south pole. Turn the loop to the other side. You can see, or go to the other side of the loop. you can see that the current is in anti-clockwise direction, and also the magnetic field lines will be coming towards your side. In this picture, the magnetic lines is going away from you, right? Then you will, at the other side of the picture, you will see that the current will be flowing anti-clockwise. This is clockwise. The current at the other side will be anti-clockwise. You will see that it is anti-clockwise, and that side magnetic lines will be flowing towards you. So that side will be north. That side will be north and this side will be south. So into the coil means that side is south. Out from the coil means that side will be acting as a north pole. Right? Right. So in a current carrying loop, what all we learned? If the current is clockwise, the end facing us will be acting as a south pole. Current clockwise, as in the figure. Current was clockwise. So you are facing south pole into the coil. Remember? Yes. And at the other side, you will see current will be flowing anti-clockwise. Remember? Yeah. That end will be north pole of the magnet. So magnetic field lines are coming out from the coil. Okay. Into the coil, south pole. Out from the coil, north pole. Right. So this is the sentence. When the electric current is passing in the clockwise direction, magnetic field lines appear to move away from us. If the current passes in the anti-clockwise direction, then we have to go to the other side. Move out from the coil. In the center of the coil. Right? Write these lines down. Now, how does the magnetic field get affected? We have to learn that. When any number of turns is increased, will the magnetic field get affected? Or if we increase or decrease the intensity of a current in the coil, will magnetic field get affected? So, to know that, we have to do an experiment. Take a paper and place a coil from A to B, and we are giving a current of a particular ampere in this coil. It is placed in the north-south direction, so that the magnetic field will lie on the east-west direction, right? Right. Either it will deflect towards west or it will deflect towards east according to the current direction, right? Right. So I am placing the magnetic compass under the conductor. So applying the snow rule, SNOW. So it will deflect towards west because current is moving now from south to north. So it deflected towards west. Now I am moving this magnetic compass towards the outer side. That is moving it further and further and further. Will this deflection stop at any point? Yes, the deflection will stop a particular point. There won't be any magnetic field, right? We have to do this experiment in 1 turn, in 2 turns, in 3 turns, etc. And note what is the difference. When the number of turns are increasing, the magnetic field strength also increases. The field also increases. As the number of turns increases, field also increases. Right? Then next, we have to increase the current intensity. The current intensity is increased. When the intensity of current is increased, then also magnetic field increases. The strength of magnetic field increases when intensity of electric current is increased. So, there are 2 points here to note. Number of turns increased, magnetic field increased. If current intensity is increased, then also magnetic field strength is increased. Now, the next topic is about a solenoid. This is the continuation of the loop. Like a loop, a solenoid is an insulated wire wound in a shape of a helix. Round, round, round. When a current is passed through it, there will be a magnetic field. So, this is a solenoid. I am passing current through it. Magnetic field is caused. There will be a south, there will be a north. How to find a south and north? Do you know? Okay, the current is passing through here and leaving here. At this coil, look at this coil. Like this will act as current when entering the coil. Take the solenoid, look at the solenoid from your side. Go and stand at this side. You will see that current is passing in a clockwise direction, then that side will be south. If the current is passing in anti-clockwise direction, then that side will be north. In the coil, when current is flowing in a clockwise direction, that part will be south, and in the coil, if the current is moving in the anti-clockwise direction, that part will be north. There is one more type to identify north and south. That rule is, when a solenoid is held at right hand, take a solenoid, catch it with your right hand, and the 4 fingers will represent the direction of current. See in the picture, the direction of current is in the direction of fingers. Then the thumb will point to the north pole. One method is anti-clockwise direction of current means north pole, and clockwise direction means south pole. Another method is coil hand must be placed in the solenoid such that all the 4 fingers are wounding the current direction, and the thumb then will be in the north pole, will be directed towards the north pole. Please write it down. This is another method for knowing which part of the solenoid will be north and which part of the solenoid will be south pole. Okay. Now the last part, factors affecting strength of magnetic. What all we have learned? When we increase the intensity of current, magnetic field of the solenoid increases. When we increase the number of turns in the coil, magnetic field strength increases. When we use a soft iron as a core, then also magnetic field can increase. The soft iron core means it acts like an electromagnet. Right? Then also magnetic field increases. If the solenoid is hollow, then there won't be much magnetic field. If we place a soft iron core inside that solenoid, then magnetic field will be greater. Then area of the wire, cross section area of the wire that we use to wound, that must be big, so that the magnetic field also increases. These are the topics we have covered in this phase. Okay, children, I hope you understood all of the topics I have taught you today. See you in the next class. Thank you. Assalamu.